Hello everyone, I'm Saurav Agarwal from the University of North Carolina at Charlotte. My paper with Professor Srinivas Akella is titled Area Coverage with Multiple Capacity Constrained Robots. In the area coverage problem, we are given a two-dimensional region which may have obstacles or holes. Holes are subregions that the robots do not need to cover but can traverse or fly over, whereas the robots cannot cross over the obstacles. The algorithms presented in this paper compute routes for multiple robots that have capacity constraints such as limited battery life. Area coverage has a wide range of applications including inspection, surveillance, and mapping. When the environment can be modeled as convex polygons, the path can be planned as a simple lawnmower or boustrophodon pattern. It is desirable to choose the direction of travel that minimizes the number of turns, as turning can be very expensive for robots. A single service direction for the entire region can be inefficient for non-convex environments. Thus, we develop a new improvement procedure for cell decomposition aimed at minimizing the number of turns. The problem becomes even more challenging when we have obstacles or holes in the environment, which our algorithm can handle efficiently. We develop a new algorithm for service track generation, which gives a set of line segments. We do not require the cells in cell decomposition to be monotone polygons, which leads to significant improvements. The algorithm can also handle polygons with holes and obstacles. The figure on the left shows tracks using a boustrophodon cell decomposition based method. On the right, we have tracks using our algorithm, which gives an improvement of over 20% for this environment. Now the question is how to traverse these service tracks while respecting the capacity constraints. We formulate the problem as line coverage, which models the service tracks as required edges in the graph that the robots must traverse. We also have non-required edges between pairs of vertices which the robots can use to travel from one point to another. Depending on whether we are allowed to travel over the subregions shown in gray, we use a visibility graph to generate the non-required edges. The formulation allows any non-negative cost function such as travel time. We also have demand functions that model the consumption of resources such as battery life, and the limit on the battery life forms the capacity constraints. The cost and the demand functions can be direction dependent due to wind conditions or uneven terrain. We solve the line coverage problem to find routes to visit each required edge exactly once, while respecting the capacity constraints for the robots. A unique characteristic of our formulation is that we allow two modes of travel. A robot services the required edge by capturing images. It can also travel without using its sensors, and this is known as deadheading. This helps in optimizing the total travel cost and resource consumption. Having two modes of travel also reduces the amount of sensor data for analysis. The problem is NP-hard, and we solve it using the merge-embed-merge heuristic algorithm. Recently, we extended the formulation for non-holonomic robots and multiple launch locations for large areas. We have made the source code available on GitHub. Thank you.